Just kidding. All right. Today, by the end of this lesson, you'll be able to know when to use velocity is equal to displacement over time, determine which kinematic equation to use, how to solve problems that involve constant acceleration. Okay. All right. So, do a quick little experiment. If you could, get your uh, stopwatches out. Get a stopwatch out. Cool. That's such a stretch. All right. So, what we have, this ramp is 1.2 meters long. Okay. I'm going to roll this bowling ball down. Okay. When I say start your stopwatch, you want to hear boom. Stop the stopwatch. On your marks, get set, go. Do you get anything? What do we get? 1.2, 1.6. Anybody else? Did you know? Here's an interesting sociology trick. Or people are more likely to drown in a crowd, like a crowd surrounded, versus just one person seeing them drown. Because everybody else is like, someone else will save them. It's proven. Okay. Get out your stopwatch. Someone else will get in. You'll be fine. Okay. So 1.2 meters, and we're going to say 1.4 seconds. The average of the two people that measured. Did the ball experience acceleration? Yes. How do you know? Yep, it's motion change. It did what inertia didn't want to do. It started at rest and now is moving. Okay, it sped up the entire time. Okay, so yes, it did experience acceleration. So how can we, I want to solve for how fast the ball is going right at the end. Like right when it gets to the end of the ramp, how fast is it going? Okay. Well, could I do this? Is that valid? Kind of seems like it. You got a displacement, you got a time, divide the two, figure out your velocity, your speed, but technically what is that equation? Your average velocity. Did it remain going 0.86 meters a second the entire time? No. So, do you think the actual, or what we, in physics terminology we call the instantaneous velocity, do you think at the end of the ramp, do you think that would be higher or lower than this? Tell your neighbor and tell them why you think so. Okay, correct answer is higher, because this captures the average which started at rest and sped up the entire time. Okay. Quick little timeout. Here's my ongoing invitation. This semester builds on itself, the entire thing. So if you're like, good thing I made it past that chapter, won't have to worry about that until the final. Not really. Like, if there's potholes in your understanding, it's going to haunt you the whole semester. So the invitation is come in, get help, let's figure it out, fix those potholes. So we got a smoother ride. Sound good? Okay. All right. So what's wrong with an approach? It gives us the average. So if I were to graph this motion of the bowling ball, and let's pretend the ramp is long enough to go 5 seconds. Tell your neighbor how you would move to make that in a motion, or in a motion detector. Like, how would you move to make that graph? Okay. Speed up in the positive direction. Good job. When we do this, what we are doing is we're saying, here's our initial point and here's our final point, and we are finding the slope. Oh dear. We're finding the slope of that line. Does that capture how fast I'm going right at the end? Is that an accurate measurement of the slope of that line right at the end? Is this how fast I'm going right at the end? No. It's an approximation. It kind of gets us in the right ballpark, but it's not the actual how fast I'm going. What could I do to make this a better approximation? How would I figure out how fast I was going? What's a better way to go about doing that, getting a closer answer? Okay. What about saying from 5 seconds to 4 seconds? Sorry, 4 seconds to 5 seconds for Mississippi. If I found this, is that better? Is that the actual? But it's a better approximation. What could I do to even make a better approximation? And the same idea, why stop at 4? Why not go to like 4.9? 1 out 4.99 to 5. 1 out 4.9998 5. Okay. That progression there is where calculus comes from. Okay. This idea that we get smaller and smaller and smaller and smaller and smaller and smaller time intervals. Okay. Problem, we don't know calculus, and you don't need to know calculus for this class. So calculus created these equations to help us out. Okay. These are known as kinematic equations. Okay. You will not ever need to memorize them. I will always give them to you on homework, on tests. Okay. They will always be available. You just need to know how to use them. Okay. Now, before you like get sick and nauseous, like, oh, like I'm out, find a variable up there that you have not seen. The, the half. I don't know what to do with the half. You've seen every variable. It's just rearranged in different ways. Okay. Okay. I will give those again. I'll give those to you. Okay. Now, when should we use kinematic equations? There'll be more. Okay. When velocity changes. If you see a problem where velocity is changing and you're trying to find the motion, kinematic equations. Okay. And in this class, we're only going to look at scenarios where you have a constant acceleration. If acceleration was changing, then that requires calculus. We're not going to go there. Okay. You have constant acceleration. Okay. So when did this equation fail us? When did this equation fall apart? Like, when should we not use this equation? Okay, yep. Not asking for the average. Also, when, like, usually I'm not going to ask for the average, but that's valid. But when what is not constant? Good. When velocity not constant. So when velocity is changing, don't use that equation. That'll give you your average, but it's not going to give you your actual or your instantaneous velocity, how fast you're going at a moment in time. But when can you use that equation? When velocity is constant. Okay, that because what that means is your average velocity is your actual velocity. If you're not changing your velocity to find the average, it's going to be whatever your speed you're going at. Okay. Good at that. Okay. All right. So let's take an example problem. Child slides down a hill on a toboggan with an acceleration of 1.5 meters per second squared. She starts from rest. How far does she travel in 3 seconds? Okay. Step one, I would draw a picture. Here's a hill and the kid on the sled. Okay. Pick your initial and final positions. So I'm going to say up here is my initial, down here is my final. I'm going to pick a direction to be positive. If it doesn't specify, I'm going to make down the ramp, I'm going to make that positive. The way she's going, I'm going to make that positive. All right, now that might seem a little weird to you. You're like, what? So far we've just dealt with horizontal stuff and then vertical stuff, and here I'm like going down an angle on a ramp. Like what? I can make, so long as we're just moving in a straight line, I can mess with that and say that direction they're moving is positive and is valid. Okay. Math teaches a little like, that's so weird, but it's doable. Okay. Now, I want you to look and identify which variables we have in that problem. And the way you do that is you look at your units. Okay. Hopefully you have this list memorized. Okay, the association between the variable and the units. Okay. If it isn't, and this is like, I would say the most important thing to memorize. If you're going to memorize anything, this is the most important thing to memorize. And this chart will grow as we learn more measurements. Okay, but making it association between the unit and the variable they represent. Okay, these are like your name tags for those variables. So you go down, he'll have accelerated meters per second squared. That's acceleration. Okay, starts from rest. Starts 3 seconds. So I've got that. Starts from rest. That's my initial velocity. How far? Good with that. Okay. Now, here's a popular wrong approach for rookie physics students. When you see a problem, like, oh, I wonder what equation I should pick. That is a premature, uh, you're looking for the right equation prematurely. Do the setup, figure out what variables. Okay, for me, I hate shopping, like, just cannot stand it. I hate going into a store and not knowing what I want to get. Like, I need a shopping list. Okay. Don't go shopping for an equation prematurely. Have your shopping list. Okay. So I'm looking for an equation that has all 4 of these variables. So I want you to see if you can pick the right equation. Thumbs up when you have a guess. Okay. Rather than having a discussion, I'm just going to open my head up and kind of give you thoughts into like, here's how I processed through this. This first equation, I don't have that, nor do I care. I have that, and I have that. Okay. But it doesn't have what I'm looking for. That, hey, I'm looking for that. That's promising. That's, I like, yeah. Initial, yep. Final, ooh, don't have that. Got two unknowns. Nope. Displacement, yes. I need that. That would be good. Initial, yeah. I've got time. So, hey, oh, hey, that. Oh, I've got that just for completeness. Final velocity, no, don't have it, and I don't care. Initial velocity, got it. Acceleration, I do have it. And displacement, that's what I'm looking for. I am looking, but I've got two unknowns there. So this is going to be my go-to. Okay. So once you have chosen the equation, here I'm requiring you to do this. I want you to rewrite the equation that you're going to use without any variables. Sorry, without any numbers. So I want you to write this. This is just a good point of communication. It'll earn you points on a test. You write that. Okay? And then we can solve. Now, here's an important but subtle detail. Anytime you have a vector, something that has direction, that you have a number, you need to assign a positive or negative value to it. Okay? Displacement we're looking for, we don't have a number, so we don't have to worry about this. Velocity is velocity of vector. Does it have direction? So we need to assign a positive or negative, but it's zero. Bad example. Time is time a vector. Does it have direction? Don't need to worry about it. Acceleration, is that a vector? Does it have direction? Yes. We have a number. We need to assign a positive or negative to this. We are speeding up in the positive direction. Therefore, the sign of acceleration is positive. Okay. For this, it doesn't really matter so much. Like, it's not going to affect our answer. I'm just trying to get you warmed up to this idea, because if that was negative, that would affect your answer. Okay. Then time doesn't have direction. So that makes sense. What I just went through there. Okay. So when you do the math, you get a half times 9. It's 4.5 times 5, 1.5. And earlier today, I've already done this calculation. I did not do that in my head. I find that to be 6.75 meters. Now, before you box that, you have one very important final step. You need to back up and say, is this a realistic answer? Is this something that could potentially happen in reality? Is this a ridiculous number? Okay, so it's like, in 3 seconds, could she possibly go 6.75 meters? It's roughly 7 meters every foot. Sorry, every meter is about 3 feet. So it's roughly about 20 feet. Could she go 20 feet in 3 seconds? Is that, yeah. I mean, it's not like, here's what would be ridiculous. That would be ridiculous. Okay. Or like 3 millimeters in 3 seconds. Or if you had like 5,278 meters. Like she'd be burning up in her atmosphere if she did that in 3 seconds. Okay, that's ridiculous. So don't just look at your calculator and write it down. Use some common sense. I don't know what you call it. It's just like make sure it's realistic. Does that make sense? I take off more points if I look at something and go, really? Boy, you didn't think about that at all. You just wrote what your calculator said. Okay? So make sure it's reality, realistic. Good? Okay. Um, the skill that I want, oh, sorry, this is just the checklist. I just talked you through all that. Okay, so that's just a checklist for your reference. Like, what should I do next? There you go. Okay. The skill that I want to build in you today is for you to pick the right kinematic equation. Okay. I'm assuming that you can figure it out, like the math part. Thumbs up when you have a guess. I don't need you to solve it. I just want you to pick the equation. Okay. Rather than turning you loose, I'm going to talk you through this, sort of. Tell your neighbor why you shouldn't use that equation. Guess. Okay, hopefully your conversation sounded like because your velocity is changing, because your velocity is not constant, because you have acceleration, something like that. Okay. Guess what's going to be one of the popular wrong answers on your next test? Using that equation when you shouldn't. But I've got all the variables. Like it fits so nice. I mean, it's just there. It's just like screaming, "Use me." Okay? But this falls apart when velocity is changing. Gets your average, but doesn't actually get your instantaneous. Okay? So I have starts from rest. I have my initial velocity 0. I have my displacement. Got my time, and I want to know how fast it's going at the end. So that's my final velocity is what I'm looking for. So I'm looking for an equation that has all 4 of those. Okay. So going through here, like, nope, I don't know final velocity or acceleration. C, yes, yes, yes. Not what I'm looking for. Time, no. Yes. Looking for it. Oh, yes. Hey! That's looking good. Just to make sure we're complete here. Final velocity, that's what I'm looking for. Initial, yeah. Oh, okay. So, correct answer is D, but it's not equal to final velocity. That's okay. You know how to do algebra. Plug in your numbers, rearrange it, solve for final velocity. Okay. Now, this is the most direct approach. You could, if you wanted to, first use C. You have all the information except for acceleration. Solve for acceleration, and then use that acceleration in this equation or that equation to find your final velocity. Valid. Inefficient, but valid. Okay, you're doing twice as much work as you have to, but it's not wrong, so long as you do the math right. Good with that? Okay. All right, give that one a shot. Thumbs up when you have a guess. Have a conversation. Okay, correct answer is start some rest, 20 seconds. Displacement, you convert that to meters when you actually do that. Okay. What is acceleration? And you would choose C. It has all four of those and doesn't have anything you don't need. How are we doing with that idea there? Okay. Thumbs up when you have an idea. Have a conversation. Tell them why you think so.
They know. Wait, no, it's not. Yeah, I'm good. That's initial. Even though the size of the rate is so obviously it's going to change it.
So that would be the initial, and then you would find the final.
He's just like, what is this? Exactly, that's why it's
Go. Initial velocity. Acceleration. How far is what I'm looking for. What else do I know? Final velocity is, you got to watch for those. Okay. So, based off of that, which equation should I use? E is the most direct approach. Good at that. Okay. Last thing, I want you to do this problem. All right, step one. Here's my car. Initial, final. I'm going to make the way they're moving in the positive direction. Okay. My initial velocity, acceleration, time, how far. Okay. Once I have those variables identified, you go shopping. Nope, don't have that. And doesn't even have what I want. I'm like that, out. Here, displacement, yes. Initial, yes. Final, no. Time, nope. Two unknowns. Displacement, yes. I need that. Initial velocity, yes. Time, yes. Acceleration, yes. And time. Ooh, third one. So I'm going to write the original equation because Mr. Smiley's a jerk and he makes me write these stupid equations without plugging in numbers. Okay. Now, check this next step out. So I am looking for this velocity. Does it have direction? Yes. I have a number associated with that, and that's 25. So I'm moving in the positive direction, 25 meters a second. So positive 25 times 3 seconds. So I don't really care about that because it doesn't have direction. 1/2 times acceleration. Does acceleration have direction? Yes. I am slowing down, moving in the positive direction. Therefore, the sign of acceleration is negative. Negative. Everybody see that? If you have a number of a vector, something that has direction, you have to specify direction. This, I'm not going to take off points because it doesn't change. This will totally change your answer. Okay? Correct answer, I think, was 56. Is that right? 52? 52 and a half. And then before we were like done, what do we ask ourselves? Is this in the realm of reality? 50 meters, half a football field in 3 seconds for a car? Yeah, that's not ridiculous. You're just trying to figure out if it's ridiculous. You're not trying to. You did something wrong. Great question. So, what happens if you get an answer that's ridiculous? You did something wrong in your math somewhere. You forgot to square something. You forgot to subtract instead of adding something. Okay. You got a worksheet due on Friday. You know how to do all of it.